Weigh a galaxy by counting its stars. Then weigh it again by watching how it spins. The two answers disagree by about a factor of 5. That gap has survived 90 years of people trying to explain it away. Guess which of the two numbers is wrong? Neither, apparently. The stars are there, the spin is real, and something invisible makes up the difference. Everything anybody can see adds up to roughly 5% of what exists. The rest has never been touched, photographed, or held in a laboratory. Fritz Zwicky noticed the problem in 1933, and almost nobody listened. He measured how fast individual galaxies were moving inside a distant cluster. They moved so fast, the cluster should have flown apart long ago. Guess how much extra mass was needed to hold it together? Hundreds of times more than the stars provided. He called the missing ingredient dark matter, and the name stuck. Colleagues found him difficult, and the result sat unused for 40 years. Being right early is worth very little if nobody can check your work. The tools to check it arrived in the 1970s. Vera Rubin picked a smaller and far more careful question. In a solar system, distant planets orbit slower than close ones, and gravity demands it. She measured how fast stars orbit at different distances inside spiral galaxies. Guess what she found at the outer edges? The same speed. Stars far from the center were moving exactly as fast as stars near it. Under visible mass alone, those outer stars should have been flung away long ago. She did it for dozens of galaxies, and every one behaved the same way. One odd cluster can be a fluke. 60 galaxies in a row is a law. Independent methods matter more than any single measurement, and here there are 3. Count the light and estimate how much mass it takes to produce that much light. Measure the speeds and work out the gravity needed to hold everything in place. Watch how the cluster bends the light of galaxies sitting behind it. Guess how well the 3 agree. 2 of them agree. Speed and bending both point to roughly 5 times more mass than the light does. Bending light is pure geometry, which makes it very hard to argue with. 3 methods, 2 conclusions, and the odd one out is the one we can see. A single collision in deep space settled the argument for most astronomers. 2 galaxy clusters ran into each other at millions of kilometers an hour. Ordinary gas in each cluster smashed together and slowed down, glowing in X-rays. Guess where most of the mass ended up? Somewhere else. The bending of light showed the mass had sailed straight through and kept going. Visible gas piled up in the middle, and the weight carried on out the sides. Whatever the mass is, it barely interacts with anything, including itself. That behavior is very hard to reproduce by rewriting the law of gravity. 1998 made everything worse. 2 rival teams measured exploding stars in distant galaxies to time the expansion. Both expected the expansion to be slowing down because gravity pulls things together. Guess what the data showed? It is speeding up. Something is pushing space apart, and it grows stronger as space gets bigger. Nobody knows what it is, so it was labeled dark energy and left there. The 2 teams shared a Nobel Prize for a result neither of them wanted. Honest people published a number that embarrassed their own predictions. The final accounting deserves saying slowly because the proportions are absurd. Ordinary matter, meaning everything ever seen or touched, is about 5%. Dark matter is roughly 27%. Guess what the remaining share is? 68%. Dark energy, about which almost nothing is known beyond its effect. Stars, planets, people, and every instrument ever built fit inside that first 5. The other 95% is named after our ignorance rather than its properties. Both names mean the same thing. We can measure it, and naming it is all we have managed. Alternatives exist, and taking them seriously is part of the job. Some physicists modify the law of gravity instead of adding invisible matter. That approach explains single galaxies rather well. Guess where it struggles? Clusters and collisions. The colliding clusters are the case modified gravity has the hardest time with. Meanwhile, decades of underground detectors have caught nothing whatsoever. Every year, the possible particle gets squeezed into a smaller corner. A confident field would have found it by now. This one keeps looking anyway. The lesson underneath all of this is about accounting, and it applies to your work. Somebody counted what was easy to count and called it the total. The universe answered that the visible items were 5% of the balance. Guess what the equivalent is in an ordinary business? Everything nobody logs. The favor, the workaround, the person who quietly fixes things before anybody notices. You feel their gravity in the results and see none of it in the report. Measure the motion, trust the discrepancy, and go looking for what holds it together.